Okay, so I received a request to go over the recitation for chapter 10 and 11. Sorry I didn't post this sooner, but now that the semester is winding down, I wanted to start trying to have some work-life balance. So I'm going to start first by I'm just going to work my way through here. So I'm going to start this first question by thinking about how do we name ethers and alcohols. So I'll start with ethers. There's two ways. One is where if we have an ether like this, and remember R just stands for any carbon chain because there's not an R on the periodic table. So actually, let me put this on a fresh sheet. So we have an R, and R means any carbon chain. And sometimes you'll see R prime or R double prime, and those mean like a different carbon chain. So it doesn't have to be the same carbon chain. Sometimes it just helps like to keep track of what's going on. But so if I was going to name this the common way, I would name first the R, then the R prime, whichever one's smaller, and then I would add in the oxygen by just saying ether. So I would name whatever the R group is. So that would be alkyl because it's a substituent. And then the other R, alkyl. And then the third one, I would say ether. And so that accounts for each side of this molecule. You can see that the yellow would be the one alkyl, the blue would be the other alkyl, and then the red would be the oxygen is the ether. So that's the sort of common name for it. So if I'm going to do the common name here, let's see. Let's say the left one, I'll do yellow, the blue, or the right one, I'll do blue, and then the oxygen O. So if I'm going to name this in the common name, I'm going to first name the thing on the left. This has 2 carbons, so 2 carbons is eth, remember? So this is ethyl. This one on the right has 1, 2, 3 carbons. 3 is prop. But this is attached in this specific Y way, so we call that isoprop. And then the YL on both of these here and here, that's because it's a substituent. And then in the middle we have ether. And now we combine them all. And I don't know if there's officially rules about if these are supposed to be in alphabetical order or not, but just in case you can always do that, A, B, C, D, E, F, G. So to combine them all in alphabetical order, it'd be ethyl, isopropyl, and then ether. So hopefully you kind of followed that way of doing the common name. Now, if we have the same thing to do the IUPAC name, which is like the formal systematic name, we figure out which side is going to be smaller. So I'll say that R prime is the smaller side, and the R is the bigger side. So we consider the bigger side to be the parent chain. Oopsie, I thought that was a highlighter. We consider the bigger side, I thought it was yellow. Bigger side to be the parent chain. And then we consider the smaller side with the oxygen to be the whole substituent. So then you just name this like it's the any other chain. So remember when we learned the IUPAC name, we learned our rules is first we identify the parent chain. And then second, we identify with the proper number the substituents. And then third, we combine it all in the proper order. So typically, the parent chain, as long as it doesn't have an alcohol or anything, it's going to be an alkane. And then if you have an R group with an oxygen, we already learned this is alkoxy. Remember, we talked about that when things are negative charge. So like sodium hydroxide, but then if we have sodium with an alkane, it's sodium alkoxide. So you've heard this before. So if our substituent would be, some kind of number, alkoxy, and then the parent chain would be alkane. So that's kind of the systematic way of naming it. So if I'm going to go back and I'll erase what I had before, just because you can pause and go back and look at it if you need to, but also because it's just kind of taking up a lot of space. So if I was going to name this in the IUPAC name, I would find the bigger side first as the parent chain. So this side has 3 carbons, so it's the parent chain. And then the other side with only 2 carbons and the oxygen now is considered the substituent. So the parent chain is what we do. Step 1, we name the parent chain. That's propane for the 3 carbons. And then we number is 1, 2, 3. We have a substituent on number 2, so either way it doesn't really matter. If we numbered it from this side, the substituent would still be on number 2. And so then our substituent is on 2, and it is an ethoxy. Eth for 2, and oxy because it has that oxygen. So this whole name would be 2-ethoxy propane. And I don't want you to worry too much about this. You're not going to have to generate the name of ethers, but you should be able to identify which ether goes with a name because it's multiple choice, So hopefully that kind of makes sense for you. I'm going to go faster through this next one, and this whole thing would be one side, and this whole thing would be the other. So for the common name here, actually, let me do this side in blue. So the common name I'm going to do it in black. The common name would be cyclohexyl, because that whole thing is cyclohexane, but when it's a substituent, we drop the ane and make it ill. And then methyl, because that's 1 carbon, so that's methane. We drop the ane and make it ill. And then ether for the oxygen in the middle. The IUPAC name would make you find the larger side. So the cyclohexane is the longer side, so that's the parent chain. Step 1, we find the parent chain, cyclohexane. Step 2, we number and identify substituents. So this whole thing now is a substituent for the IUPAC name. And it's the only substituent, so when we number, that should be number 1. So it would be 1-methoxy. Technically, if it's on a cyclohexane ring, you don't have to put the number 1, but I think that is ridiculous. So I sometimes still do it, and I know that's against the rules, but what can you do? So, and then step 3, we combine this all, and we would get 1-methoxy cyclohexane. So that would be the IUPAC name. Okay, now let's go into naming alcohols, which we covered this actually back in chapter 4 when we first learned naming. So this should be more of a review for you. So this parent chain is 7 long. Remember, the parent chain has to contain the alcohol, and this one does. So 7 is heptane. And then let's try numbering it in the other direction, see if that gets us something different. 1, 2, 3, 4. Nope, it's either way, our substituent would be, our substituent is the alcohol, and it's 4-all, either way. So then when we combine this all, it would be heptan 4-all. Another way is sometimes it's 4-heptan-all. I've seen people do both. Both of these are considered correct by IUPAC. Either of those is correct. So either way, if you did it, that's right. And I just changed the color so you could kind of see where it came from. Okay, next one. Let's see. 1, 2, 3, 4, 5. So I find a 5-membered chain. I do want to check out, just because there's 1, 2, 3, 4. So there is a way to get a 4-membered carbon chain, but 5 is better. So, and I don't see another way to get a longer one. So that's the parent chain is pentane. And then when I see my substituents, it looks like they're on 3. I like to number in the opposite direction just to check. 1, 2, 3. They're on 3 either way, so that's nice. And then what are my substituents? There's a 3-methyl, and there is a 3-ol. So now I'm going to combine this all. This is a suffix. It's going to go at the end, and this is a prefix, so we don't have to worry about alphabetical order. We can just say 3-methyl pentan 3-ol. And another way you can do it is 3-methyl 3-pentanol. That's also correct. Either one of those is right. You can put the 3 either right before the alcohol or before the whole pentane. Okay, so that's for the naming. The next one is draw the reaction mechanism of the following acid-catalyzed ring opening of epoxide. So I will start with the curved arrows. We know that there's lone pairs here on this oxygen, and that will be drawn to this H+ if it's acid-catalyzed. And that is going to result, I'm going to use a smaller thing just so that we can see things more easily. That is going to result in, I'm actually going to take away the stereochemistry because I'm not going to test you on stereochemistry for the final, and so I'm not going to worry about it. One of these electrons right here made this new bond, one of these lone pairs made this new bond to that hydrogen, so that's where that comes from. But now with this partial positive, there is a strong pull of electron density towards the oxygen because the oxygen doesn't want to be positive, and that leaves an absence of electrons behind on these 2 carbons here and here. However, because there are 2 carbons here, there's more electron density to give from this side, which means this side is going to have the stronger partial positive. So because that side is going to have the stronger partial positive, that's where the oxygen in the nucleophile is going to attack, and then this ring will open. So this is a very similar mechanism to oxymercuration. And it's also a similar mechanism to that halohydrin formation or the bromonium ion. That's what you get in the halohydrin, the bromonium and then oxygen attack. So if you're curious for a similar mechanism, that's a similar mechanism. It almost functions the same as an SN1, but without rearrangement because there's only a partial positive. So if this nucleophile attacks, I'm going to draw back over this arrow in yellow just so you can see it. This nucleophile attacks, then this bond right here will break. I worry that that's kind of crowded, hard to see, so actually I'm going to erase some things here and try to make it a little bit easier for you to see. Okay, so so we have a lone pair here, but when this attacks from here, the oxygen, a new bond is going to form here, but you can't have that many bonds to carbon, so this one's going to break, and so you end up with nothing has changed on this side of the molecule, but over here, our leaving group is no longer attached to this side. We got rid of it. The bond broke, so that bond is not there anymore. It acted as a leaving group, but it's still attached over here. Nothing happened on that side. The 2 methyls that were already there stay there, and then you get an oxygen, and it's 2 hydrogens. Now this is 3 bonds to because of the formal charge, 3 bonds to oxygen. It's positively charged, so we get this structure, and then it will deprotonate, and you get an OH here and an OH here. So that's the overall reaction mechanism. You get this structure. this is the kind of reaction I use BLAM for, and that's if it's acid catalyzed. If it's acid catalyzed, which this one is, that little bit of acid catalyzes the reaction, then the nucleophile attacks the most substituted side. Now, the second question is, does this rearrangement take place? Does rearrangement take place in the reaction above? Why or why not? And the answer is no, it does not. And I already described why, but just to demonstrate how I would expect you to write an answer if you had a free response on a question like this, it would be something like, no, rearrangement does not occur because there is not a full carbocation that forms. So rearrangement cannot happen. Something like that. Okay. Draw a mechanism for base catalyzed opening with the same starting material above, but using NaOH as the nucleophile instead. Okay, so if I was going to do that, again, I'm going to take away the stereochemistry because I'm not going to test you on that, or at least I'm not for this semester. What is this? Fall 2024. Okay, so the nucleophile in this one, base least, acid most. So the base likes to attack the least substituted side. And the reason for that is there's no protonation, and without that protonation, there's no partial positive to be attracted to. So instead, this is more about sterics. The nucleophile wants the less hindered spot, just like in an SN2 reaction. And this mechanism is exactly like an SN2, where it'll find the less hindered spot, the nucleophile, oh geez, just turned my thing sideways. The nucleophile will attack on that less substituted spot, and then the leaving group will leave just like in an SN2 reaction. Now, usually O- doesn't act as a good leaving group, but because epoxides are so high in ring strain, it will act as a good nucleophile. Ugh, apparently I just need to lock this screen. It will act as a good nucleophile here or a good leaving group here, because it just wants to break the strain of that ring if possible. So your O- has attacked over here, and it became, your O- here attacked right here, and it became this. And then your leaving group is right here, and it's here. Then we would usually add some kind of acid to get OH here, and then also OH here. You still have your methyls in this. So you end up with the same product, but by, in this case, same product, but by a different mechanism. And that matters if your nucleophile isn't alcohol, because if your nucleophile, for example, is OCH3 minus, and here it would be HOCH3, because it would be in acidic conditions, then instead of alcohol here, you'd get OCH3. And this one, your nucleophile attacked on the other side, so instead of alcohol here, you would have gotten OCH3 on this side. And so you would have gotten different products. So in this case, you got the same product, but that isn't always true. So I just want to kind of draw your attention to that. Okay, at which side does the nucleophile attack? I actually already answered this question, but it attacks on the less substituted side because there's, oh, listen, I already wrote it out. If this was a test I was taking, I would write it nicer. It's the less substituted side because without the acid catalyzing it, there's no partial positive, and so it's more attracted to the side with less steric hindrance, not the side with the strong partial positive. Okay, next question. Draw the stepwise mechanism of the given reaction. So this reaction will occur first with acid catalyzed OH, because you have oxygen with acid, and then you get your Br minus, and now this has become a good leaving group. So now what we have here is a electrophile with a good leaving group, and we have Br minus as a strong-ish nucleophile. So now it can attack, and it's likely to go in an SN2 reaction because we have a negative nucleophile and a primary leaving group. So this Br minus is likely to attack here and then kick out this whole leaving group. And I actually had some people kind of struggling with that. But if it was like this, I think it would be easier for you to see. And that whole thing was the leaving group, and your Br minus attacked here. And then this left, and we got a new bond to the Br. That might be easier for you to see, but just instead of water being the whole leaving group, it's this alcohol becomes the whole leaving group. So we end up with getting our, I did not follow these steps. This was step 1. Sorry. And then this was step 2, as detailed. So we have our OH acted as our leaving group plus CH3Br. Now the next question, that was with one equivalent. The next question would be OH plus H plus gets you OH2 plus, and then your Br minus would come and attack and kick this leaving group out, which this one I think people have an easier time seeing. It's this exact same reaction mechanism. What we just saw here is the exact same reaction mechanism that we had up here. Okay, so we would get this plus this, and water was our leaving group. Okay, for the, I don't know why this says reactions pairs. For the pairs of molecules below, indicate which is going to be more acidic. Make sure you can explain why. So the first thing I will think about usually with acid-base is pKa, just so I know which one, or sorry, is my pKa table, just so I know which one is going to be more acidic. So immediately looking on these, I'm saying this alcohols are 16 to 18s and amines are 38 usually. Alcohols are 16 to 18. Carboxylic acids are 4 to 5 usually. Alcohols are 16 to 18, and alkanes are 50 usually. So I already know which one is going to be more acidic in each one of these cases. This is more acidic because the smaller the pKa number, the more acidic it is. This one's going to be more acidic, and this is going to be more acidic. So I know that without even, I have those numbers memorized just off the top of my head, and I know that without even checking. I know which ones are the most acidic, so I can do that. But then make sure you can explain why. When I think about the why, that is really important, and that's something that I want, a skill that I really want y'all to have. And so 2 big whys are the inductive effect and the resonance effect, and then also just electronegativity in general. So if you think about the periodic table, we have you can think about electronegativity going across the row: carbon, nitrogen, oxygen, and then fluorine. So this is the most electronegative. These are least electronegative. Now, this does not work if you're going down the periodic table. You can't think about electronegativity in that way, but you can think about electronegativity in this way. Once you're going down the periodic table, you're adding the element of the radius getting bigger, so it doesn't exactly work the same way. So we can't think about it this way, but we start, because they're adding layers of orbitals in this example. So we can't think about it that way, but if you only have the same level of orbitals, you can kind of compare electronegativity. So when I think about this oxygen giving up its lone pairs, its proton, and becoming, you know what? I want to say one more thing before I get into this. So these are the things we can think about. But The other thing I want you to think about is, what is acidity? When I think about acidity, especially this is a Bronsted definition, it is, I lost an N there in Bronsted, the ability to give up a proton, or willingness to give up a proton. And that is largely determined by how well can you handle the lone pair, because what a proton is a hydrogen atom without its lone pair, right? How well can you handle the lone pair left behind? So I think I used to think about acidity as like, oh, we're giving up an H, but an H atom is a proton, like hydrogen is a proton with 2 electrons. That's what the hydrogen atom is made up of. I don't know why this is there. Okay, that's what the hydrogen atom is made up of. So if that's what our hydrogen atom is made up of, if we give up just the hydrogen and not the 2 electrons, that's what I mean when I say we give up a proton. And so acidity is how well can you deal with the electrons left behind. And I'm actually going to add in a blank page. So how well can you deal with the electrons left behind? And there's 3 big things that I typically think about. And one is inductive effect, which can help spread the impact of the lone pairs left behind. Second is resonance effect, which can also spread around or delocalize. Both of these delocalize the electrons, or like spread them out. Maybe delocalize is maybe a specific resonance word, but they spread out the impact of the negative. And then the other is across a row only, because you have to think about other things when we're adding layers of oxygen or of orbitals. But across a row only, you can think about electronegativity. Like, how willing is it to keep those extra electrons anyway? Does it want extra electrons? So a lot of our examples, we have carbon, nitrogen, oxygen, and then fluorine. And so electronegativity increases across this row. So as electronegativity increases, so does willingness to be negative, basically. Willingness to take on electrons. And so when we're thinking just of the base example of a carbon chain, an amine, or an oxygen, and then they lose a proton, so they lose a hydrogen and leave the electrons behind, leaves an H atom, leave the electrons behind. So we have an H, base comes and takes it, and it leaves the electrons behind. Base comes and takes it, leaves the electrons behind. Base comes and takes it, leaves the electrons behind. We end up with these structures. Oops, I drew too many here. NH minus and O minus. And if you're wondering why these are negative, it's about formal charge, and you can go check out the video I did on formal charge not too long ago. So when I look at all these, carbon is the least electronegative here. So it's the least willing to be negative. Nitrogen is the next least electronegative, so it's the next least willing. And then this is the most electronegative of this pair, and so it is the most willing, or of this set, to give up electrons. And that explains the trend that we learned with our pKa's. So we don't just have to rely on those numbers, but we can understand that oxygen is the most willing to give up its protons because it's the most electronegative. So that would be the explanation I would give for A, is that oxygen is more electronegative than nitrogen. So when comparing atoms on the same row, electronegativity could be a big determiner in willingness to deal with the electrons left behind. Now, that answers kind of A, and it also answers C pretty well. You'd have to really be able to, if you were like writing that as an explanation, be able to clearly communicate that, the electronegativity across the row, because there are some examples where something is more or less electronegative. Like, I think we had a question that was something like this on a quiz, and a bunch of people said that nitrogen would be more acidic here because it's less electronegative or something like that. I don't remember exactly. But it was like, yeah, well, nitrogen is always less electronegative, but sometimes it's less acidic, so that's not a good explanation. So make sure you have a full explanation that is really logical if you're writing out explanations like this. Not that there's going to be that on your final, but anyway. So then that explains both of these, A and C. But now looking at B, if B lost its electrons, it would look like this, the alcohol. But if the carboxylic acid lost its electrons, these both have the same atom. So this oxygen is the same thing that gets the electron, so it's not about electronegativity. So what other things could spread the impact of this negative charge and make it more able to handle it? Well, one is resonance. So instead of each oxygen being fully negative, each one of these oxygens actually only have about half a negative in reality because of the resonance structure. But also, even when it is in, we'll say like in this one, there is the added effect of the inductive effect because there's a partial positive here. So it's like pulling the electrons away. So this one, B, I would say, is more, the carboxylic acid is more acidic, both because of the resonance and because of the inductive effect. Okay, the next one, predict the structures 1, 2, 3. That should be 1, 2, 3. 1, 2, 3, 4, and 5. Sorry. Okay, so the first one is acid catalyzed hydration, and this is something that I think I talked about this on your practice final, but you can kind of run through all the reactions we've learned so far. So the first one is acid-base, and then the second ones we learned were SN1, SN2, E1, E2. And then the third one is addition reactions. And the fourth one we learned are radical reactions. Addition reactions or alkene reactions, I guess maybe is broader. So when I try to figure out what's going to happen, I think about like, okay, is this an acid base? Well, I do have an acid, but I don't have a clear base. So I don't know about that one. So I'm going to probably say no. For SN1, SN2, do we have a good leaving group? No. And you can't do SN1, SN2 on a sp2 hybrid, so that's unlikely. E1 we could do, but again, we don't have a leaving group. So it can't be any of those. We need a good leaving group. Then the next thing I think is additions, alkenes. This is an alkene, so this is probably going to be some kind of radical reaction. Or sorry, some kind of addition to an alkene. For radical, you need a radical forming species and an initiator. We don't have that. So I'm pretty confident this is going to be a reaction of an alkene. And so that's how I decide this is acid catalyzed hydration of water. But also, you can think of these excess electrons here. There's 4 electrons shared between these 2 carbons. That's a little bit of extra electron density. And then there's an absence of electron density on this proton. So that is part of why it's attracted to that. So the proton will add, forming the most stable carbocation. We call that Markovnikov or Markovnikov. I don't know what's the proper thing here. And then, so we get Markovnikov addition. And then, sorry, my neck is kind of hurting, so I'm switching positions. Hopefully you can still hear me pretty well. we have a carbocation. And anytime there's a carbocation, you should see a carbocation as a red flag. This is a red flag that says, oh no, there's a carbocation, rearrangement could happen. Anytime you see a carbocation, rearrangement could happen. Not a partial positive, a full positive on a carbon. So sure enough, there is a hydrogen right here that could trade places with that carbocation and shift over, and then we'd get our hydrogens here. It's implied, so we don't have to draw them both in, but our hydrogens are there, and our carbocation has now moved to the middle. And that's where our water will then attack. And so we'll get, it's not really proper to draw that pointed up, so I'm going to change it and draw OH2 plus, and then it would get a deprotonation step. So I'm going to go back over here. For part 1, the answer to the acid catalyzed hydration of this species is this answer. And then the next thing we learned was SOCl2. SOCl2, when I'm thinking about that, I'm like, well, this is not obviously an acid-base reaction. Can't be an SN1, SN2, because going back to my list over here, that's where I am right now. I'm on this list. I need to get that app where you can circle things, but it's hard to get it on UNT's iPad. Okay, and then it can't be in addition to an alkene because we don't have an alkene. Unlikely to be a radical reaction because we don't have an initiator. And I forgot the 5th type of reaction, which we learned was reactions of alcohols and epoxides, alcohols and ethers. Alcohols and ethers. So we learned the reactions of alcohols and ethers. And so did we learn something in alcohol and ether chapter with SOCl2? Yes. SOCl2 or PBr3 do the same thing by an SN2 reaction where the alcohol is the nucleophile. So actually, I guess it sort of is an SN2 reaction, although it's not immediate obvious because there's not an immediately obviously good leaving group. The SOCl2 is actually the good leaving group. And so it goes by an SN2 reaction that you don't need to know the details of, but it does invert stereochemistry if we had stereochemistry, and converts the alcohol to a chlorine. So that is the SOCl2 step. So you need to know both of these reagents. You need to recognize them for your final, but you don't have to know the mechanism for them. So now we have this alkyl halide, so that's the answer to part 2. If we react this with H2O and heat, now I'm going to go back to my list of reactions that we learned, and I don't see this as an acid base right away. There's not a clear acid, but it is a good candidate for SN1, SN2, E1, or E2 because there's a good leaving group and water can act as a nucleophile. But with heat, if I'm thinking about my decision tree, heat's going to go elimination. We have a weak nucleophile, a tertiary leaving group, so I think this is going to be E1. And so we'll get this carbocation right here, and then probably water will steal this and give us a new alkene as our answer for part 3. Then I see this, and this is not a carboxylic acid. It has 3 oxygens, and if it has 3 oxygens, that is a peroxy acid, similar to MCPBA. And I went through a list in class of here are all the things you're going to need to know for MCPBA. You should be able to recognize the structure. You should be able to recognize the word peroxy acid or MCPBA. All of these will essentially just get rid of that double bond, and right where that double bond was, they'll add in an oxygen, and it will retain stereochemistry if you're worried about stereochemistry. So this would be technically, which I didn't make you do it, but technically we had the alkene was trans, and so this would be a wedge and this would be a dash, just so that you know, but actually no, I did that wrong. These two are on the same side, so these would both be wedges and this would be a dash to keep the stereochemistry the same. Okay, but I'm not going to make you do that. I just want you to, you need to know to retain the stereochemistry, but I'm not going to ask for the stereochemistry after you open the epoxide. so that doesn't matter as much. But the next step for ring that we have here with epoxide is we learn 2 ways to open an epoxide. I'm going to add a page here. We learned 2 ways to open epoxide. One is acid catalyzed and one is base catalyzed. Did I get that structure right? Yes. And this is acid catalyzed ring opening of epoxide with HOCH3, I believe. Is that right? And then base. So this is the first step, and the second step is NaOH. And the way I know it's ring opening, or an acid catalyzed ring opening of epoxide is it has H+, and then we have an epoxide. So those are the only things we learned how to do with an epoxide. So those are the clues that kind of tell me what reaction that I'm looking for. And the first step on this is to protonate the epoxide. And now remember, there's a strong partial positive on the more substituted side. So this OCH3 is going to act as my nucleophile attack there, and this bond will break. So this is very similar to the question that we started with today. We have our OCH3 on one side, H on the other, so positively charged. This bond broke, but the other side didn't. So we have O here, H, and now it's neutral because it gained some electrons. And then, sorry, I had an alarm going off. Hopefully it didn't impact this. So then we have our methyl group is still, it helps on these to, sometimes I worry about losing my carbon. So I'm just going to number the carbons and make it a little bit easier to see. And students often lose their carbons. And that leads them to getting the wrong answer on multiple choice questions. It's like, it feels like this looks right, but you don't realize that you've lost a carbon along the way. So I strongly recommend that you number it. So just to go back and look, our carbon number 4 still has the alcohol attached to it, so that's right. And then carbon 3 has the methyl here with the protonated methanol, so that looks right. So we're in good shape, I think. And then this carbon 5 attached to carbon 4, so that looks good. And then the next step, so that's, we use this reagent and this reagent. Now we have NaOH, and with NaOH, that is going to act as a base, and OH minus with an acid, because this is positively charged, just like hydronium. We have a easily accessible proton, and that is our deprotonation step. So we've talked a lot about how deprotonations, you don't always have to worry about like showing the mechanism or what happened with that, but I did have a lot of students ask me what the base was for, and that's part of the workup. So like when we have an organic chemistry reaction, we don't want any charged species at the end. If I'm trying to like make a new thing in organic chemistry, I want it to be neutral and stable on a shelf and not reactive. So if we end up with something positive, like this was positive, to get it back to neutral, we'll add just a little bit of base and cancel everything out. So then instead we just have water. And we, of course, would have some Na plus floating around in there. And we'd probably have some, if there's any like negative species from before, like maybe the Cl minus. So you'd end up with like water and table salt. So that's what that base is. And so those are the things that it's like I want you to think about. Not just like, okay, and then protonation magically happens, but how deprotonation happens. And so that way you'll always know, like, why is this here? It's part of the workup to get everything neutral. Okay, and then the last step, the last question is, for each of the following reactions, propose the reagents you'll need to synthesize the following alcohol. So this is retrosynthesis, and the goal of this is for you to think about how to get the transformations that we want. And so when I look at that, I see we start with an alkene and we end with an alcohol. So this is an addition of water. The alcohol is added where the original alkene was. It's added on like, let me just number it so that it's easier to see. I'll erase this. When I look at this, I think, okay, we have 1, 2, 3, 4, 5 carbons here. And then on this one, we have 1, 2, 3, 4, 5 carbons here as well. So there was a double bond between carbon 3 and 2, and that has gone away, and in favor of that, we've added this alcohol. The alcohol is in the same position that the double bond was on, so there's no rearrangement. And we learned to add an alcohol, or H on one side, OH on the other, 3 ways. There's 2 without rearrangement. One is Markovnikov and the other is anti-Markovnikov. So is this added Markovnikov or anti-Markovnikov? Well, the alcohol added to the more substituted side, so that's Markovnikov. So there's one way to add an alcohol Markovnikov without rearrangement, and that is with HgOAc2. Water. You have to make sure that water is your solvent. If you had a different solvent, the first step would be not oxymercuration, but alkoxymercuration to make an ether. And then the second step, the demercuration, I can never remember the second step's reagents, is, I think, is it NaOH and NaBH4? One of them is NaBH4 and the other is H2O2, and I always get it mixed up. So that would be the kind of thing, if I was taking my OChem final, and when I did take my OChem final, if I was a free response question, which yours won't be, so you shouldn't have to worry about that because the second step will be given to you, I would write it down right before I took the test, because it's like, oh, this is something I consistently forget. So I'm going to make sure I have it. So as soon as I get the test, the first thing I do when I get tests is I write down anything that I'm prone to forgetting so that I won't forget it and I don't have to worry about remembering it later. Another trick is, if you're not sure about something like this, and you want to what would that be? You can look at other multiple choice questions that have that in there, and that can maybe sometimes have the right answer for you. Okay, so that's what I would do, is I would do oxymercuration, demercuration to get this transformation. Now the next one, we see a similar thing if we label our cyclohexane between carbon 1 and the methyl substituent. We have added, we've gotten rid of our double bond, which used to be there. That's now gone. We've added an alcohol. It didn't move. It's on the same position as the original alkene. So it's, again, no rearrangement. Then I'm going to consider, is it Markovnikov or anti-Markovnikov? And it is on the less substituted side. So this side has 2 substitutions. This side has a hydrogen and hydrogen. So this is the less substituted side. So this would be BH3 with THF, and then H2O2 and NaOH. So that would be, the first one is oxymercuration, demercuration. And the second step is hydroboration, oxidation. Okay. The next one I see, I like to, just when I'm doing this, the first thing I do is I compare what changed. So I see that on this side we have an iodine, and on this side we have an alcohol. So I'm going to number this 1, 2, 3, 4, 1, 2, 3, 4. We have a methyl here. So we didn't gain or lose any carbons. All we did was trade out this iodine for this alcohol. And so to me, that looks like a substitution. And now we can decide what substitution reaction would be best. Would it be SN1, SN2? Well, this is primary, and we can't do an SN1 with a carbocation on a primary. Even if we could, it would rearrange, so that won't work. So the primary makes me think we need to promote SN2 reaction conditions. So I think we should use NaOH because it's narrow, it's a strong nucleophile, and it would be able to come in and attack here and kick out here and trade out the nucleophile, OH minus, for the leaving group, and you'd also get plus I minus. So that's how I would approach that one. This last one, again, looks like we've added alcohol. It looks like there was a double bond right here between the methyl and where the alcohol is added. So again, this is probably addition of water without rearrangement. It looks like it added alcohol and a hydrogen, and it added them syn, and it also added it anti-Markovnikov. And we know, again, one way to do that, and that would be the same as the second question. So BH3 and THF, and then H2O2 and NaOH. So this is, again, hydroboration oxidation. Okay, so question 7, draw the steps in the radical reaction mechanism between Br2 and methylpropane. So the first thing I'm going to do is draw those out because I don't know what methylpropane looks like just in my brain. I'm actually going to draw these in black. I don't know when I switch to blue, but I like the standard color here. Br, and methylpropane, so 1, 2, 3, and it's 2 methyl, so it looks like this. So the first step, the initiation step, we would need heat or light. I put them backwards. This one's light, H nu, this one's heat. And then that would break apart this Br2, and you would get 2 radical bromines. So that's the initiation step. Initiation takes no radicals and turns them into radicals. Propagation makes a new radical. It sort of like consumes one radical and makes a new one. I made a joke in class and it works really well. It's like a new radical from old radical is just like a phoenix rising from the ashes, right? We're not propagating like plants where we take one plant and make several more. We are consuming one in flames, and from the ashes rise a new radical. So a radical propagation step could easily look like, and oftentimes with bromine, it's going to happen where I'm just going to pick one of these and these. That's what I redrew in this next step. It's going to form, more selectively form the most stable radical. So, and the most stable radical, similar to carbocation, is the most stable carbocation that will form. So the most stable, if you know where the most stable carbocation will form, that's where the radical is going to form with Br reactions. So you can see this radical is going to combine with 1 electron from the bond between hydrogen and the propane, and leave the other propane radical behind, or propane electron behind, and then the H and Br add together. So I'm going to like color code all these. Let's make 1 red and 1 blue. Those are making up the bond between the hydrogen and the hydrogen and the propane. So now a new bond is formed with the electron between the bromine and the hydrogen, and then this radical left behind was from the original bond between the methyl and the hydrogen. So hopefully you can kind of see where all those came from. And then a termination step would be adding 2 radical species together to end the radical reaction. So how do I make this go away? Oh, I think like that. Okay, like this, and I can move it up there. Yeah, okay. So if we had this radical species from here, and the other Br from here, these two could combine and make a bromine. And so whenever I'm approaching these questions like on a test or something, insert blank page, I honestly, it's like I will just, if I see Br2 and heat or light, I just first think, where's the most stable radical going to form? Right here, and then that's where the bromine will add. The bromine radical will add. So you should know all these steps so that you can identify them. Like there might be a test question that'd be like, which one of these describes the steps shown? And it'd be an initiation, propagation, something, and you have to label it. But so you should know the mechanism and know those steps. They really come in handy for polymer chemistry. Polymer uses radical reactions a lot. As long as you can kind of know in general where the alkane or where the halogen would form, you should be able to answer those questions correctly on your final. Okay, well, I hope this was helpful for you, and I hope your studying is going well, and I look forward to seeing you when we take our final next week.